As you stand at your window, looking out at a sky filled with dark clouds that are pouring down sheets of rain and hail, suddenly it happens. A twisting column of gray descends from the clouds. At first, it's just hanging there, suspended above the land, but it soon reaches down and makes contact with the ground. At the same time, it turns even darker as it picks up dirt and debris. If you're lucky, you make it to a shelter before you can witness the immense swirling winds pulling up animals, cars, and buildings in its wake. This harsh reality can occur anywhere in the world. However, by a wide margin, most tornadoes happen in the United States, more than if you combined the yearly average number of tornadoes in every country in the rest of the world. The US is also the only country to regularly experience tornadoes that reach the highest classification of violent, which cause the highest percentage of deaths. Each year in the United States, there are over 1,000 reported tornadoes, and on average, these result in around 80 casualties. But some years, it's much worse, like in 2011. The 2011 super outbreak was the largest, costliest, and one of the deadliest tornado outbreaks ever recorded, taking place in the southern, midwestern, and northeastern United States from April 25th to 28th. It resulted in roughly $12 billion in damages and left an estimated 321 people dead. Tornado deaths are caused when an individual is picked up by the strong winds or when they're struck by a large chunk of flying debris. While the death rate is significantly lower than it was in the early 1900s, the seemingly random and spontaneous nature of tornadoes makes them one of the most difficult to predict weather phenomena. Current forecasts of incoming tornadoes only provide an average of an 8.4-minute lead time. And in a scenario where not only your possessions are at stake, but the lives of you and your family, every second counts. How and why do some tornadoes become so destructive, and just how big can they get? And how might we one day be able to predict them better? For such a well-known phenomenon, we know surprisingly little about how tornadoes actually form. And understanding how they form is crucial for developing better tornado prediction models. Some scientists risk their own lives by getting up close and personal with these violent storms, all in an effort to determine exactly what's happening in and around the tornado. Most tornadoes begin with a supercell, a storm with a persistent rotating updraft at its core. Supercells form due to a particular combination of winds, when wind speed and direction are different at different altitudes. This is called wind shear. When wind at ground level is blowing one direction and wind higher in the atmosphere is blowing another direction, it can cause a horizontal tube of air to form. Then, as warm, humid air rises and cool air falls, the horizontal tube of rotating air can be pushed to become a vertical one, called a vortex or a mesocyclone, which can have a diameter of 5 to 20 kilometers. At this point, the whole storm starts rotating, and the supercell is born. This type of storm is the parent of most tornadoes. Near the ground, the mesocyclone can be narrowed by the strong updraft. This process, called vortex stretching, speeds up the circulation. This creates a funnel cloud. Then, the downdraft brings the rotation down to the ground, and a tornado is born. Low-pressure systems in the US pull warm, moist air from the Gulf of Mexico and cool, dry air aloft from the Rocky Mountains or the high desert in the southwest, creating consistent wind shear. The states that fall between these regions end up being in the ideal location for severe tornadoes to form. But this is all a bit of an approximation. Exactly what the right conditions are for tornadoes to form is still a bit of a mystery. In an effort to answer the many questions remaining about tornado formation, the NOAA National Severe Storms Lab launched a research project in 1995 called the Verification of the Origins of Rotation in Tornadoes Experiment, or more simply, VORTEX. There were several iterations, the largest of which, Vortex 2, took place in 2009. It included over 100 scientists who used cutting-edge equipment to analyze weather measurements taken around supercell thunderstorms across 10,000 miles of the southern and central US, an area dubbed Tornado Alley. Over the span of 1 month, they collected data from 11 supercell storms, including one supercell tornado. The results from this project indicated that tornado formation is related to the temperature differences at the edges of the spinning air. But that might not always be the case. Mathematical models and real-life observations have demonstrated that tornadoes can arise with very little temperature difference. Clearly, there's a lot more to uncover on exactly what makes a tornado form. How they dissipate is not much clearer. Scientists are still debating the details, but generally, a tornado stops when it loses its source of instability, like heat or moisture, or its vorticity. One way this could happen is by encountering a cold flow of wind from a rainstorm called an outflow. But of course, it's what happens between its formation and dissipation that's really important. How much damage did it cause? How many lives did it take? Just how destructive was it? This is what a tornado's rating is based on. After a tornado has ended, experts examine and tally up the damage. They look at what type of buildings were affected and how badly they suffered. They then use the enhanced Fujita scale to assign a rating from 0 to 5. This assessment is also used to estimate wind speeds, varying from 100 to over 320 kilometers per hour. And assessing the damage is often the only way scientists can estimate how strong a tornado was, since it's rare that they're able to take a direct wind speed measurement. And sometimes the damage is absolutely catastrophic. Out of those that have had their wind speed directly measured, the tornado with the highest wind speed began in Bridge Creek, Oklahoma on May 3, 1999, during a massive tornado outbreak involving over 70 tornadoes. This particular EF4, EF5 tornado traveled across heavily populated areas in Oklahoma, and with wind speeds topping 512 kilometers per hour, it completely obliterated over 200 homes over the course of 1.5 hours, killing 36 people. It was classified as an EF5 because the EF5 category has no upper limit. But its wind speeds were so fast, some scientists think it should have fallen into its own new category, an EF6. The problem with creating an EF6 category is that the vast majority of structures are simply gone at the EF5 rating. And besides the rare tornado like the Bridge Creek Moore tornado that has its wind speed directly measured, the rating comes from the destruction it leaves behind. And complete and total obliteration looks the same if the wind was 350 kilometers per hour or 550 kilometers per hour. Scientists believe that theoretically the fastest tornado possible on Earth would be 611 kilometers per hour. The Bridge Creek Moore tornado was not far off. But while the Bridge Creek Moore tornado certainly was devastating, it was not even close to the deadliest. On April 26, 1989, a single tornado in Bangladesh took at least 1,300 lives and left 80,000 homeless. It was estimated to be an EF4 tornado, with wind speeds of 338 to 418 kilometers per hour. The devastation was so complete that except for some skeletons of trees, there were no signs that there had ever been any standing structures. And the deadliest tornado in US history was the Tri-State tornado on March 18, 1925, which resulted in a death toll of a whopping 695 people. One tornado killing almost twice as many as the super outbreak in 2011, which was made up of 300 separate tornadoes. The Tri-State tornado's name comes from its journey from southern Missouri to Illinois to Indiana, totaling 350 kilometers. This also made it the tornado with the longest path, which took about 3.5 hours. During this time, it destroyed 15,000 homes, earning it a ranking of an EF5. But with a maximum width of about 1.5 to 2.5 kilometers, neither the Tri-State nor the Bridge Creek tornadoes were the biggest tornadoes in history. The widest ever recorded reached an absolutely massive width of 4.2 kilometers. This occurred around El Reno, Oklahoma on May 31, 2013, and lasted about 40 minutes. Luckily, it remained mainly in rural areas and was rated an EF3. So while winds reached 484 kilometers per hour, its damage was limited. Wide tornadoes aren't usually the deadliest. However, this one did result in the deaths of 8 individuals, 3 of which were the first storm chasers ever to be killed in a tornado. These deadly events are a bone-chilling reminder of just how ruthless nature can be. For anyone who lives where tornadoes frequent, all they can hope for is a fair warning to get themselves somewhere safe. Currently, meteorologists can identify weather conditions that could result in a severe storm days in advance. But determining exactly when or where a tornado will form is much more difficult. A lot of that difficulty is due to the relatively small scale of a tornado. While storms can cover large areas, even multiple states, tornadoes are usually less than a kilometer wide. Once a storm forms, predicting a tornado becomes a lot easier. Using Doppler radar systems, meteorologists can watch a storm and provide a risk assessment for a certain area. Something like, there's a 20% chance of a tornado over these 40 kilometers. Most often, tornado warnings made by the National Weather Service turn out to be false alarms. This happens up to 80% of the time. Of course, it's always better to be safe than sorry, especially when you only have a few minutes to prepare when a tornado does end up forming. But can we do better? While most people would run from a tornado, it's a storm chaser's job to get in front of it. They set up scientific equipment along what they hope will be its path that will take important measurements as the tornado travels over it. As we've already discussed, there are still a lot of unknowns about how and why tornadoes form. But we know a lot more than we used to, and that's thanks to these incredibly brave individuals, most of whom are meteorologists, including one of the storm chasers who lost his life in the El Reno tornado. His name was Tim Samaras, and he was extremely passionate about his work. He once said that a ground-based measurement taken from within a tornado is especially crucial because it provides data about the lowest 10 meters of a tornado, where houses, vehicles, and people are. Other scientists have agreed that the rapidly changing conditions low to the ground may be what's controlling a tornado's formation. This data could not only help scientists to better understand tornadoes, but would improve their forecasts and help design structures that are able to withstand intense winds. But of course, making a technical instrument that can withstand these winds itself is no easy task, and scientists had once given up on it. That was until May 7th, 2002, when Tim Samaras deployed a probe of his own design that survived a direct hit from an EF3 tornado while recording changes in pressure, wind speed and direction, and air temperature and relative humidity. With this device, he and his team went on to collect video and data from inside several tornadoes, providing the scientific community with invaluable information. But collecting this data is just one piece of the puzzle, and scientists are still developing better detection methods and warning systems. These include new types of radar technology, such as phased array radar, which can scan the entire sky in less than 1 minute, 5 times faster than current radar systems. Scientists are also building better forecast and prediction models. These use current weather and radar data to simulate what the atmosphere will look like in the future. To make them more accurate, scientists are trying to increase their resolution, because not only are tornadoes small compared to thunderstorms, but what's happening inside a tornado, changes in temperature,